So this is the session 4 for the module 2 of the response spectrum topic. In this session we're going to see about the forced vibrations for the single degree of freedom system. So here the force is there and also the degree of freedom is single, only one is there. As usual, the forcing function will be also there, inertia force is also there. So because of the force, obviously displacement will going to take place, stiffness force is also there, damping force is also there. Now you look into the equation of motion. In the equation of motion, the force is also present, means the force vibration is there, forcing is there, so that's why the force is also present. Now let us see that here in this cases, so whatever the displacement or the solution equation is there, which is a second order ordinary differential equation, whatever this one is there, equation number 1 is there, so it's a second order ordinary differential equation, and according to the its mathematical solution is that it includes both CF, that is a complementary function, which the solution is obtained by taking the RHS in the equation 1 as 0, then the equation whatever it is obtained is nothing but the free vibration case is there. Whereas PI means the whatever the particular solution. So this particular PI is the solution obtained in which direct linkage with the forcing function Ft. So whatever PI is there, so particular solution. So in this case it is related with the force only. So whatever the force here is there, so here the force is applied with the a dynamic force, varies with respect to time, and whatever the forcing function Ft is there, so it's a harmonic function. Harmonic function means it is with respect to time and also the sine, the harmonic is there, that's why it is a sine function is there. So that is Ft is equal to forcing function is F naught into sine of omega t. So here F naught means initial displacement and omega means natural frequency, t means the time. So here these are the whatever the notations which are used over here. So now whatever the equation number 1 is there, so you can put it F is equal to F naught into sine of omega t. So that is equation number 3. Now using the terms, so we will be having the whatever the n is there, it is nothing but c by 2m is there, and the p square is equal to nothing but k by m is there, where p is the nothing but natural frequency. Now you can just substitute all those things in this equation number 3. Both the values of c by 2m means you have to divide it by the m, so that you will be going to get the equation number 4 after dividing the with respect to m, dividing with respect to m. And now you will be having the total equation whatever 4 is there, its solution is nothing but, solution means displacement solution, that is a complementary plus particular equation. So particular equation, that is equation number 5. Now here whatever the x component is there, x of the CF, okay, complementary function is there. So already in the free vibrations in the last the whatever the topic we have seen, same thing will be there, whereas the particular solution will be written as a cos of omega t plus b sin of omega t. So now whatever the particular solution is there, again we can rewrite in this way, and here whatever the x value is there, you just note down here x double dot is there, means 2 times we have to do the derivative function of that one. So according to that the equations will become this one, whatever the a minus a omega square cos of omega t minus b into omega square sine of omega t. You can substitute in the earlier equation number 4, you can substitute here, and whatever the forcing function is there, sine of omega t, you can have the simplifications of that one, you can simplify it, and you can see that the whatever the cos part is there, sine part is there, whatever the this part is there, cos part is there. So now that one is comparing the equations, coefficients, that why you have to put it is equal to 0, and similarly other part whatever this sine part is there, so that also you can put it as f divided by m values. So now you just simplify the values of this particular whatever the equation is there, and here you will be having the a and b's values are there. So now you just simplify the a and b values after the putting the boundary conditions, so that whatever the at a time t is equal to 0, the displacement is equal to 0. So like that, putting the boundary conditions, so will be have a value, this one, a is equal to minus 2n b into omega divided by p square minus omega square is there, and similarly after putting the other boundary conditions, we will have b value. So now you will be having a value, and whatever the b value is there, you just substitute here a and b values. So this particular whatever the equations we will be having, it is called as a trigonometrical equations, that is a cos phi as well as sin phi, so that you will be having the particular solutions. So now after simplifications, the particular solution is f naught divided by m into square root of p square minus omega square whole square plus 2n omega whole square into sine of omega t minus phi. So that one is the particular solution equation is obtained. Now whatever the displacement equation is there, x is there, we can see it here, and here we'll be having a certain the factors we have to assume wherever the omega pi by p is there. Omega means nothing but the natural frequency or the exciting frequency is there, p is the natural frequency, the ratio of exciting frequency to the natural frequency. So you can say that it is a nu, that is nothing but the frequency ratio. The frequency ratio is, if it is equal to 1, that is called as the resonant frequency ratio. So that is here the whatever the beta is nu is there, nu divided by p is there, so that is nothing but the damping ratio, and whatever the m p square is equal to k is there. Now you substitute the corresponding value, the equations will be like that. In this equation, f naught by k is called as static displacement. Static displacement is nothing but initial force divided by the stiffness, that is the static displacement is there. Now you can rewrite the equations like that. And now since for the maximum displacement, when the maximum displacement is there, when the sine of this particular omega t minus theta is equal to 1, if it is 1, then you will be having maximum displacement. Hence the maximum displacement will be when this particular sine function will be 1. So you can rewrite the equation as the maximum amplitude values as x maximum as sigma st divided by square root of 1 minus nu square into whole square plus 2 nu into chi into whole square. So like that you can write it. Now the then after this one, so you will be having one ratio, that is a DLF, that is called as the magnification factor. So this magnification factor is nothing but the ratio of the displacement due to the static the displacement, that the ratio is there. So that's why maximum DLF will occur when sine function is equal to 1. So 1 divided by, so when this omega t minus pi is equal to 1, so maximum displacement will be takes place. So that is called as maximum dynamic load factor. So that is given by in this equation. So that is mu. So mu is nothing but DLF, dynamic load factor, magnification factor. So now in order to get the mu, so you will be having the du mu by du nu. So you just substitute the values and according to that you will be having the equations. That is nu is equal to 1 minus 2 chi square. So now Here the whatever the phase angle is there, it is given by this one, and then after simplifications we will be having pi is equal to the whatever the phase angle is there. You can put it in this pattern, tan inverse of 2 chi nu divided by 1 minus nu square. Now what is studied here from this the forced vibration is that, and that also the forcing function is the harmonic means it is a sine function, means sinusoidal curve is there, whatever the effect will be there, sinusoidal curve effect is there, that is a harmonic function. So usually the machine forces whatever the machine will revolve with some revolutions per minute, so definitely it will exert the harmonic type of loading. So now finally what it is concluded is that from this the free vibration part is a transient and vanishes the force part when it persists, and if the increase of the damping ratio, the magnification factor is decreases, and also the magnitude of the maximum value of the magnification factor is very sensitive to the value of the damping ratio, then the steady state vibration is independent of initial conditions of the system. So this is all about the how the different the calculations which are involved in finding the responses of the forced damped single degree of vibration is concerned. So now you will going to see one the part is that effect of frequency, input, motion and resonance. So the what is the resonance? Resonance is nothing but a phenomena of increase in the amplitude that occur when the frequency of periodically applied force is equal to very close to natural frequency of the system on which it acts. When oscillation force is applied at a resonant frequency of a dynamical system, the system will oscillate at higher amplitude than when the same force is applied at other non the resonant frequency. You can see that from this figure you will be having the frequency ratios. What are the frequency ratios? The exciting frequency divided by the natural frequency, that is nothing but the frequency ratio. If it is a 1 means the both the frequencies are same, then what will happen? The transmissibility is nothing but the amplitude is going to be increase. Suddenly you can see that there is a boost up of amplitude, and this amplitude is going to reduce whatever the frequencies at which the amplitude is maximum is known as resonant frequency. Resonant frequency are resonant frequencies of the system. Small whatever the periodic forces at the near the resonant frequency, the system will able to produce large amplitude of oscillations in the system, and this is due to the shortage of vibration energy. And here you can see that for the different damping ratios, the amplitude how it is going to happen, that is the resonance, the frequency is that is the transmissivity, means how much the maximum displacement will take place. So here the whatever red is there, it's a damping ratio is very less, and as the damping ratio increases, what will happen? The amplitude is going to reduce. You can see that 10%, 3%, 1%, 0.5%, so like the different damping ratios, how this whatever the damping ratios or damping coefficients, how it will going to impress makes the displacement is going to be reduced. So this is all about the effect of resonance, that is two frequencies are same, that is excitation frequency as well as natural frequency, how this one two frequency ratio is 1, that is the effect of the resonance, that we can see it from this figure. Now we'll see some numerical examples from this forced single degree of vibration is concerned. Forced single degree of vibration is concerned. So here a problem is that a machine of mass 1.95 kg vibrate in a viscous medium. So it is asked to determine the damping coefficient when the harmonic exciting force is 24.46 Newton, which is results the a resonant amplitude of 1.27 meter with a time period of 0.2 second. So here it is a resonant case. The resonant case means the whatever the frequencies are there, expression frequency and natural frequency is equal to 1. So we can call that one as also the beta, that is frequency ratio, we can write down as beta. So according to our calculations, so whatever the static amplitude is there, static displacement is there, nothing but f naught by k into 1 minus 2 chi. So what is the chi? Chi is equal to c divided by cc is there. Okay, you rearrange the equation so that a naught is equal to we can have f naught divided by c omega n is there, or a naught is equal to f naught divided by c omega we can use over here. Then here it is a given that the time period is 0.2 second is there. Hence the frequency is 1 divided by t. 1 divided by t is nothing but 5 CPS or a hertz, 5 cycles per second or a hertz. Now what is our natural frequency? Natural frequency is equal to 2 pi f is there. So f is 5 cycle is there. Substitute here so that you will going to get natural frequency as 31.4 radians per second. Then what is the amplitude is given? Amplitude is given as resonant amplitude. How much it is? 1.27 is there. So now the resonant amplitude, whatever it is there, okay, so it is known, and f naught is known, so that we can calculate the c. C is equal to f naught divided by a into omega n. Okay, so f naught is known, that is a whatever the force is there, okay, initial force. So whatever the initial harmonic force is 24.46 Newton is there. You substitute here, that is it is a given data 24.46, and a naught is just now we have this seen it as in terms of meter. Amplitude, resonant amplitude is 0.0127. Omega n is calculated as 31.4. Substitute here so that we will going to get the whatever the seismic damping coefficient. The damping coefficient C value is 61.33 Newton second per meter. So that is the value of the C, that is the damping coefficient, so which is asked in this example. Now let us take another example, that if the same example number 1 is excited by the harmonic force is there and the frequency is 4 cycles per second. 4 CPS means 4 cycles per second. What will be the percentage increase in the amplitude of the force vibration when the dashpot is removed? Dashpot is removed in the sense dashpot is nothing but damping is removed. Okay, so meaning of dashpot means in the single degree of freedom system we have shown one dashpot. Okay, so that is a damping. So that is the notations for the damping is nothing but dashpot, that is C is equal to 0. Here if the dashpot is removed, that is nothing but the damping C is equal to 0. Now the whatever the frequency is there, 4 cycles per second is there, that's why the natural frequency omega n is equal to 2 pi f is there, so 25.13 second is there. Now the frequency ratios, whatever the frequency is there, so here it is a given the 4 cycles, the forcing function is this 4 cycles per second is there. Okay, so now here we are having the at C is equal to 0, so we will be having the f is equal to 5 seconds per second is there. So now here we will be having the f as well as fn is there, both the ratio is 0.8, so both the ratio is 0.8. Now whatever the omega n, that is natural frequency, is 31.4 just now calculated. Now the one more relations, the omega n square is equal to k by m, so make it omega square is equal to k by m, so that we will be having k is equal to m omega n square. So m is so here in this earlier problem m is given 1.95 kg is there, so substitute here 1.9 the frequency whatever 1.9 whatever the weight is, mass is there, substitute here, omega n square is also there, so that stiffness is calculated. The first a naught is that no damping is there, no damping is there. So no damping means nothing but F naught divided by Km omega square. So substitute F naught, K, M and omega square we will be having. Under no damping cases the displacement amplitude we have calculated. Now the whatever the A naught no damping you will be having the ratios with the ratios of A naught no damping versus the damping. So both the ratios are given here. Both the ratios are given. The earlier problem also the resonant frequency 1.27 is there, means 0.027, and whatever the no damping cases the amplitude is there. The ratio is nothing but multiply by 100 is equal to the whatever 278. So 278% under no damping cases the displacement is going to increase. Displacement or amplitude is going to increase by 278 percentage. So this is all about the example related to the resonant under the two cases of the non damping and damping. Now next problem is that a weight is attached to a spring of the stiffness 525 Newton per meter has a viscous damping device. When the weight is displaced and released, the period of vibration is found to be 1.8 second and ratio of conjugate amplitude is 4.2 to 1. Then determine the amplitude and phase when the force is F is equal to 2 cos of 3t acts on the system solution. So now let us see that what are the given data. Here the stiffness is given, K is equal to given, that is 525 Newton per meter, and also two successive ratios of the amplitude is given, 4.2 to 1 is there. So now two successive ratio is there, obviously logarithm decrement is going to happen because damping is there here. So now here whatever the logarithm decrement delta is equal to ln divided by the whatever the ratio is there, you substitute the that particular values. Now you will be having the delta is equal to 1.435 or it is approximately is equal to 2 pi by j. So that what j is nothing but damping ratio, whatever 1.45 divided by 2 pi. So you will get damping ratio as 0.228. And here it is given that the whatever the period is there 1.8 second is there. So time period Tn is given. So if the Tn is there 1.8 second, then the frequency is nothing but 1 by Tn. So that you will be get 0.55 cycles per second. Since Fn is there, so omega n can be easily calculated. What is omega n? Omega n is equal to 2 pi of AF. So F is substituted. So that you will going to get so much of radians per second. Once omega n is given, square it and nothing but it is a K by M. K by M or M is equal to K divided by omega square. So K is known, omega n is also known. So you just substitute the both values. So mass is calculated. Mass is 43.1. Now here applied force is 2 cos of 3t is there. Now according to the single degree of freedom harmonic excitation, now the amplitude is given by F naught by K into 1 divided by square root of 1 minus beta square. Beta means the whatever the ratios of frequencies. So here F naught is equal to 3 and omega is equal to 3. So that's why the whatever the frequency ratio is there. So we will be having 3 divided by 3.49. 3 divided by 3.49. So whatever the omega n is there 3. And the 3 is there, it is associated with the this 3. Okay, omega t, omega divided by omega n. So whatever the cos of 3t is there, so 3 means the omega by omega n. Omega n is natural frequency, to frequency ratio is 0.86. You substitute the F naught, K value, beta value is there, square it, and also damping ratio just now calculated, so that you will going to get so much of meter amplitude. So that is nothing but 8.11. And also the phase angle is the equations can be again written as pi is equal to tan inverse of 2 j beta into 1 minus beta square into whole square. So now the phase angle we can calculate tan inverse values as 80 degree, means this is a phase angle. So this is all about the problem of this particular example. Now let us see the other example, that here it is said that a spring of mass excited by the force F naught is equal F naught into sine of omega t at a resonance of amplitude is measured to be 0.58 centimeter. At 0.8 resonant frequency, the amplitude is measured to be 0.46 centimeter. Determine the damping factor Chi or the damping ratio of the system. So here what else given in the problem is that the frequency ratio is given, means 0.8 is a resonant frequency, means frequency ratio beta is equal to 0.8, and whatever the maximum amplitude A max is given as 0.58, maximum amplitude at resonant is given 0.58. At whatever the beta is equal to zero point 0.8, so the amplitude is said that it is the 0.46 centimeter, 0.46 centimeter. So whatever the magnification factor is there, according to this equation 1 divided by 2 j into square root of 1 minus j square is there. So now it occurs when beta is equal to, if substitute beta is equal to 1 minus 2 j square, now the magnification factor is again written as m is equal to 1 minus square root of 1 minus beta square into square plus 2 into chi beta square. You substitute and you just two ratios, you divide it one by one. Whatever the m max is there, that is also known to us, m is also known to us, you just divide one over the other, so that you will be having m divided by m. So you just substitute these values as well as the denominator values, so you will get 1.26 is there for value of the smaller damping ratios. So whatever square root of 1 minus beta square whole square by 2 chi is equal to 1.26, means this particular value, okay. So you can see here. So then, or you can substitute the damping ratio in the beta values as well as the j values, okay. So sorry, this beta values and j you just put it as it is, so that is equal to 1.26. again you can simplify here, so that you can have the whatever the damping ratio is there. So damping ratio, so these two ratios, so we can have the 1.26 is there, and after simplifications we will have a small damping values, so you will be having 1.58, okay. So now after that you just rearrange the equation and solve for the damping ratio. So finally the chi value, okay, after simplifications of solutions of this equations you will get chi is equal to 0.187, means damping ratio is calculated as 0.17. so after simplification, okay. So this is all about this example. Now next example is that in this problem it is said that a forced vibration test under the harmonic excitation, it was noted that the amplitude of motion at a resonant was exactly 4 times at the exciting frequency, 20% higher than the resonant frequency. Determine the damping ratio of the system. What is given is that whatever the exciting frequency is there, A naught is there, the resonant, so it will become 4 times of this one, 4 times of the whatever the initial value is there. So when they the whatever a naught dash is there, so now also it is said that the exciting frequency is 20% higher, means whatever the frequency is there, exciting frequency is there, it's a 20% higher, means 1.2 times of natural frequency at the resonance, and that's why the frequency ratio is nothing but 1.2. frequency ratio is 1.2 according to the amplitude values. maximum amplitude is equal to f naught by k into 1 minus square root of beta square whole square plus 2 chi beta square. You substitute over here, beta value is 1.2 is there, f naught also the values you can have the f naught, then the whatever the denominator value is there, k is there, so k you can write down as c omega n into n, okay, and to whatever the ratios are there, okay, maximum to this one, so that ratio a naught by a naught dash is there already, it is said that it is 4, so you just substitute 4, and in this case the only the damping ratio is the unknown, damping ratio was the unknown. So now solve for the damping ratio, so that is 0.058, that is a damping 0.58, or you can put it as 5.8% as a damping ratio. So this is all about how the damping ratio is to be calculated. Now next one is the figure shows that a steel rigid frame 1 by 1 story having the hinged supports carries the a rotating machine. This whatever the escorts, what will happen here, a horizontal force at the girder level is forms the 50,000 sine of 11t. So 11 means here it is a omega, that is the exciting frequency, so much of Newton, assuming 4% critical damping, damping is 4%. Then what is the steady state amplitude of vibration for the column I for the column, okay, I for the column, I is equal to 1500 into 10 raised to minus 7 meter fourth, and E Young's modulus is 21 into 10 raised to 10 Newton per mm square. So here there is a AB is a one column, CD is a one column, and it is a resting for the a mass of the 5000 kgs, 5000 kgs is there, and whatever AB is there and CD is there, it's a 4-meter height, 4-meter height is there. Now the whatever the stiffness is there, since both the ends are hinged, that's why the stiffness is given by 3ei by L cube, 3ei by L cube. L is known, okay, L is known as a 4-meter, so you substitute of the 4-meter, E and I also given, so that the stiffness K is equal to 3ei by L cube, so that is calculated as 2953125 Newton per meter. So once the K is known, mass is also known, the natural frequency is square root of K by M. So K is known, mass is given as the 5000, that is the mass is given, so substitute over here, so that you will going to get natural frequency as 24.3 radians per second, and whatever the damping ratio is there, 4% is given, 4%, so that is chi is equal to 4% means 4 divided by 100, that is a 0.04, and whatever the nu is there, so here it is 0.453, 0.453, so already in the previous slide we have seen, and now the maximum, whatever the maximum, the amplitude is there, maximum amplitude is f naught divided by k into the whatever the frequency ratios is 1 minus nu, so nu is also known 0.453 and chi is also known, so that we can have the maximum displacement as 0.0213 meter, or you can put even 21.33 mm. So like that the numerical examples is to be solved. So in this session you have seen that how the forced vibration, here the forcing function is the harmonic force. So here we have seen the harmonic force which is acting on a single degree of freedom with the damping and without damping also. If the chi is there, so if damping is there, if the chi is equal to 0, it is called as undamped cases. Also we have seen the resonant frequency, means two frequency ratios, resonance, that concept also we have seen, and also dynamic magnification factors, so like that, and the number of some numerical examples we are seen with the forced vibrations of single degree of freedom of a system.